Welcome to the next session. The session is Optimizing OAK Repository Search. I want to give a short introduction. My goals for the presentation are reporting experiences that we made in upgrading from CRX2 to OAK at our customer systems, and show some best practices for optimizing OAK repository search performance. My name is Olaf Jentsch. I'm a software engineer at Conrad AG, and I've been working with DayCQ, later AEM, since 2006. That is the agenda for the talk. I want to give a short description of our customer's situation. After that, I want to have a long talk about migrating repository search to OAK. After that, I want to give some notes how we did the measuring of search improvements. And at the end, I want to give some hints about very useful tools that support excellent development of search functionality. Let me start with our customer situation. They had different systems, some of them in CQ5.6.1, some of them in AEM 6.2.0, and they started a migration project with AEM 6.2 as the migration target. What means the key challenge was the change from the underlying repository from CRX2 to OAK. They have large repositories with more than 1 million documents with at least 500 gigabytes of data. They have their websites, their web applications containing certain search functionalities consisting of both XPath and SQL2 queries. And the declared requirements for the migration were the search features should be the same after migration, and the search performance should be improved. So now I want to talk about migrating repository search to OAK. We have it done in these 4 steps. The first step is achieve your queries to run. In other words, when you have successfully made the content migration with live content or representative content or at least good test content, then try out your application-specific queries and look at the system response. It might be that the query run into an exception because of syntactical changes that have been made in the OAK implementation, not in the query language as a whole, but in some details. I will show an example in the next slide. The second step is ensure your queries to use indexes. You will notice when your query doesn't use an index because it performs slow. Also, you can recognize that it doesn't use an index by a warning message that occurs in the log file that tells you consider creating an index. But creating an index is not the only option. Basically, there are 3 options from you can choose from to reach that the query uses an index. Go to the third step, optimize index definition. When your query still not perform fast enough, or when you need in your application advanced search features like full-text search, excerpts, facets, and so on. And step 4, optimize index definition, optimize the queries itself. Often this step is done together with optimize index definitions, alternating this optimization and then the other optimization, and so go ahead to improve performance. Here is my example for the first step. When you get a query parser exception, running a query, you have to adapt syntactical changes. Look at this query, example query. It was very common in CRX2 to write the filter conditions one behind the other as a sequence as they come from input, for example, from a search formula, and then you write that enclosed in square brackets as a sequence of filter conditions. Now you have to write explicitly the AND operator and enclose all around with square brackets. There are this kinds of changes you have to do to adapt to the syntactical changes. It's not very difficult to do that, so the first step can be done very quickly. The next step, ensure your queries to use indexes. As I said before, the system will tell you when your query doesn't use an index by that warning message. Also, you can use one of the tools provided by AEM. One tool it's called Explain Query Tool. It's a very nice tool. You can use that to know if there is there used an index for your query or not, and which index is used. Is no index used, then there are basically 3 options to reach that your query uses an index. For the more simpler queries, my advice is to prefer to use the out-of-the-box indexes. That can be done eventually by slight change the query or by slight change an existing out-of-the-box index. There are certain circumstances that let you decide to create your own custom indexes. For example, if your application constantly searches for a certain custom property, something like an identifier you are looking for every time, then create your custom property index. Custom property index is not that interesting. I will mention more about the more interesting case. If you need some of the advanced search features, like searching for multiple properties, full text search, aggregation of properties, then create your own custom index, a Lucene index, which provides all the settings to work for the more complex queries. That's an example where you can apply the first option. That's the query above is a query that worked fine in CRX2. It worked fast. It was looking for a general node type anti-base, but now in OAK it's a traversal query. That means it's very slow. It doesn't use an index. So when you simply change the node type the query is looking for to a more specific one, you achieve that this query will be executed by the node type index, which is an out-of-the-box index and will be fast. Let's look at another example. It's the example where you can apply the other option to slightly change the out-of-the-box index. That's a full text query combined with a property condition. The query looks for node type CQ page, and the special problem with this query is it even uses one of the out-of-the-box indexes, what is called CQ page Lucene, but it finds nothing. Why it finds nothing? It's because that out-of-the-box index is a property index which cannot deliver results for a full text search. So go to the index definition. That's what here is shown as a part of the index definition notated as JSON. Change the definition by setting analyze true for the property you are looking for with the full text query, and already it works and is fast by this slight change to the existent index. As I said before, there are circumstances when you have to create a custom index to reach that your query uses an index and works fast and find results. My first recommendation, if you do that, is define the index not at the root level, but at deeper nodes, exactly where your content, the content of your website is located. So you restrict the scope of your index. You are sure that your index will not be used for queries searching for a different content path. Also, you reduce the amount of data for the index itself, and you avoid conflicts with system queries and out-of-the-box index, especially when your index definition contains one of the general node types, anti-base or CQ page or CQ page content. Then make sure that your index is not used for system queries, which might have an impact on the system behavior. My next recommendation is include all properties that you are expressing filter conditions in your query, include all that properties into the index definition. That looks like that. It's again a part of the index definition included all these properties you are looking for. When your queries run, when they use the intended index, but still are too slow, then go ahead and optimize your index definition. Now I don't want to mention all these properties that are possible to set in definition. There is a good documentation for the Lucene indexes. I want to look at the advanced search features. Starting with full-text search. As you have seen before in my example, it's only set analyze true for a property to be able to make a full-text query. That means think about that carefully. Put all properties you have that contains text you want to be searched for with a full-text query. Put all that with these settings into the index definition, including those properties that comes from subnodes of GCR content. So shortly, what provides the full-text search, you can see a search term. It demonstrates what the full-text search can do. It deals with wildcards. It deals with negation. It deals with phrases. Keep in mind that the full-text search of OAK takes your search term as AND operation, only AND. All results that the query gives you are documents that contains all conditions, where all conditions matches that you have expressed in your search term. Let's look at facets. It's very simple. Add the setting facets true for all properties for which you want to extract facets for. Let me mention another interesting thing. We have encountered a problem in AEM 6.2 out of the box while setting facets true to a multi-value property. But we could solve this problem by updating the AEM with the latest fix pack. So I recommend stay updated, keep your system updated, look at informations about new releases. They could bring the right bug fixes for you, and they could bring, of course, new features. So how facets looks like, I don't have to talk about that. Let me show how easy it is to use for a developer. In the query debugger tool, if you know that, it's a very good formula. You simply put an additional property, in this case region, and you could get the facets from this query debugger. Using the Query Builder API, it's also very easy to get the facets. Simply create a new predicate with a lot of constants, put in your name of the property you want to have the facets for, and then add that predicate to the query and get the facets simply by the getter method from the query result. It's very easy. It's a nice feature to use. Excerpts. Again, it's very easy to define the index definition, especially for that feature. Simply use an excerpt true to all the properties. My recommendation is put that setting to all properties you have defined for full text search in order to get excerpts from that content you are looking for. Very important if you are using excerpts is that you put that special property called rep excerpt in the index definition. It makes your query fast. Otherwise, looking for excerpts will a little bit slow. A short look at suggestions. My recommendation is to define a separate index, especially for suggestions. And then put all properties you want to have suggestions from into the index definition, set them use in suggest true. And don't forget, in the general part of the index definition, to set suggest analyzed true, because otherwise you would get whole property text as suggestions, what could be very long, but normally you want to have single words as suggestions. So coming to optimized queries, the main reason for optimization of queries is to improve the performance of a query. In OAK, the default query language is SQL2. All queries are translated to and executed as SQL2 queries. So one optimization could be to switch from XPath queries to SQL2 directly, so you can avoid translation costs. Translation costs are not that high, but at least the parsing step and the optimizing step are omitted. Because of the automatic translation of XPath queries generates for all conditions, generates many union select statements, you can avoid that creation of many union select statements by writing directly an optimized SQL2 query. The next option to make your search fast is modify the filter condition in order to reduce the number of conditions or to find simpler conditions, what will lead to better performance. Let's look at this example for switching from XPath to SQL2 language. Here is the original XPath query. Contains OR and AND conditions. And what the automatic translation will generate is that statement. It consists of 9 union select statements. Imagine you have a large repository. Every single select statement needs time. So here you need much more time with 9 union select statements. So what you can do is to write manually the query in SQL2, optimize that directly in SQL2, and this query looks very similar to the original query in XPath. But it only consists of 1 select statement, so it only once uses the hopefully optimized index, and it's much faster than the other way. Now another example, a real life example that came from one of our customers. It came already from the old system with the following requirements. There is a deep content structure inside a CQ page. That means a very hierarchical mix of text and lists and download nodes. And the required result type for a search where only the CQ page content nodes and the download nodes. And the result ordered by GCR score. So let's look how the content could look like. You see the GCR content node. It contains text properties. You see at level 4 the text node with text properties. You see at level 6 the download node with text properties. You have this full text query, and because of you are looking for download nodes as well, which are from type anti-unstructured, you have to filter all the results to reduce the result set to only the node type CQ page content and download. That means your query contain one OR condition, and as I said before, that leads to 2 union select statements after the automatic translation. So another disadvantage of this query separated in 2 select statements is that in the result list at first comes the results of type CQ page content ordered by GCR score, and behind that a list of download nodes ordered by GCR score. But that is not what you want. You want an overall ordering by GCR score. So we found a simple solution. Add a further property to both nodes, to nodes of the both types, CQ page content and download nodes. Ideally, there is already an existing property that you can use. Ideally, it makes sense to even show that property in the search result. Obviously, this property has to be mandatory or should be automatically set at node creation time, and it has to be included in your index definition. The content could be like this. You add the further property, the region property, to the CQ page content nodes and to the download nodes. In order to create that property for sure, you can use you can implement an event handler that automatically sets that get the event at creation time of the download node and sets automatically with some inheritance logic the value of the parent CQ page content node. So you are sure all nodes has this property, and you can simplify your query by replacing the OR condition with only one and very simple condition, the exist condition, and so you regain great performance and the sort order as well. So some notes about how we did the measuring of search improvements. We did it by the old way, comparing the timestamps of log messages. Also, we used the time output that does the query debug log. It tells you the query time, it tells you the facet extraction time, and we recorded all that timestamps in the old very good Excel sheet. It has always been a good tool for statistics, so we used it. What I can recommend is after all performance tests with queries, run them at a system with live content or nearly live content. Because at a developer machine, you don't see bad performance, you don't see even an improvement of performance. So you have to test that with live content. That's very important. Then, after every single step of optimization, run the same queries and record them in your Excel sheet or whatever you use to get a better look for the improvements, to get better, to know better what you has reached already and what is left to do. Select queries for this tests which are representative. That means queries that give many results, queries that give only a few results, queries that give a moderate result set. Finally, some hints for the tools we have used. At first, there is the query debug log. It's a kind of configuration for a special logging for all the query implementation packages of OAK. If you set that at debug level, it puts out a lot of information about all you need: the query execution time, facet extraction time, index update time, about your query itself, and so on. It's very useful. Then, as I mentioned before, the explain query tool is a part of a bigger set of diagnosis tools provided with AEM 6.2 out of the box. And this tool is very good if you want to know which index is really used for my query. And another recommendation, use that tool also at the customer system with the many live content, because the index selection process while query execution could work a little bit different at a system with more content, because the index selection depends also from the amount of nodes that are indexed. So assure that your index is used also at the customer system. Another nice tool is the query debugger. The query debugger is it's a formula which is very fast. It has no overhead. It gives you all output you need for development of the advanced search features, facets, excerpts, pagination. It's a very good tool, and it in contrary to the CRXDE, which is also good, the query debugger shows you all results even if your query is slow. The CRXDE doesn't show you results if your query is slow, or if your query gives a lot of results, then the CRXDE Lite is not the choice. So again, the query debugger, use that, get used to it, because the search criteria has a special notation. So at the end, I have a list of some useful links to the tools I had mentioned and to documentation of the OAK implementation of Lucene indexes and so on. You can get that from the slides, download from the slides from the adaptTo site. So now, have you any questions?
Thank you, Olaf.